we will consider yet another difference between these two models. In the case of the car, the model of the system will be fairly complicated. The inputs and the outputs will be related by many equations which are nonlinear. On the other hand, the model of the lever is given by a linear equation. Since these angles are the same, we can confirm that knowing the current value of the input y1 is enough to know the current value of the output y2, and that this equation is linear. You might think that this system is linear because it is static, while this one, being dynamic, is necessarily nonlinear. This is not so. Let us consider a very simple dynamic system which is linear. This system consists of a mass m connected to a fixed wall by a spring and a damper. Let x be the horizontal position of the mass, and let x equal to 0 be a position such that the mass is in repose. Let there be a force F acting on the mass. We know by Newton's law that mass times acceleration is equal to the sum of the forces applied on this mass. This force F, which of course can change with time, is only one of the three forces acting on the mass. We will also have the force exerted by the spring and the force exerted by the damper. If the mass moves to the right, the spring will exert a force to the left. Consequently, the force of the spring will be equal to minus a constant multiplied by the position of the mass. Here we have used Hooke's law, where this constant is a characteristic of the spring. Likewise, the damper will exert a force to the left, and that is why its force is equal to minus a constant multiplied by the velocity of the mass. Here we have used Coulomb's law, and this constant is a characteristic of the damper. Here we have a model which is given by a differential equation. This system is not static, it is dynamic. That is why we need a differential equation. And the first and second derivatives of x require a knowledge of what has been taking place in the past. That is why a differential equation is a model of a dynamic system. Notice, however, that this differential equation is linear. Let us consider another system which is also modeled by a differential equation and is consequently dynamic. The voltage or electric tension imposed at this point is the input of the system. The voltage or tension at this point is the output. We know that there will be a current that passes through these two components. We know from Ohm's law that the resistance Likewise, the capacitance of a capacitor is equal to a quotient. In this case, the voltage at the terminals of the capacitor will be Vout minus 0. We want to eliminate the current from these two equations, since we want to relate the input and the output without this needless variable. Again, we reach a differential equation modeling the system, and this differential equation is linear.